Hello Year 10 GCSE students, I hope you are well. Today's lesson is on energy systems. How do we create energy for our muscles to contract so that we can play sport? As always in this lesson, if you can tell me what, or basically describe and explain written in red, then you can access the lower grades. If you can tell me how, written in blue, then you can access levels 5 and 6. But if you can tell me why, then you're accessing the higher levels. You're becoming critically evaluative. You're analysing and evaluating. Okay, so before we start, it's important that you have some idea of the only usable form of energy in the body. And the only usable form of energy in the body is something called adenosine triphosphate. That's simplified down to ATP. So it's one adenosine and 3 phosphates, ATP. How I'd like you to remember it is like a champagne bottle with the cork in. When the cork's in the champagne bottle, there's potentially lots of energy. In our body, enzymes are biological catalysts and they tell the ATP to break down. For a champagne bottle, you flip the cork with your thumb, the cork pops off, it explodes off, and you get energy. Well, it's similar for ATP. When an enzyme tells the bonds of ATP to break, we get energy. And it's that energy that allows me to see you now, allows me to speak to you, allows me to stand. It certainly is the energy that allows me to run, to kick a football, for my hair to grow, for my skin to be healthy. The ATP is the only usable form of energy. We have a problem though. Once ATP has been used, when we've popped the cork off the champagne bottle, we can't use the ATP again until the cork is put back into the bottle, or until ATP is rebuilt from ADP, that's 2 phosphates, plus the spare floating P that is flown off when we broke the bonds. So, how do we get the cork back in the bottle? How do we rebuild ATP? Well, that's what today's lesson is all about. It's about eating food fuels to give us energy to rebuild ATP so that we can use it again. Because remember, ATP is the only usable form of energy in our body. Now, there are 2 anaerobic ways of rebuilding ATP, and there is one aerobic way of rebuilding ATP. Remember, aerobic means with oxygen and anaerobic means without oxygen. Alright, so let me bring you to a golden substance right from the off. My golden substance is glucose. It's the golden fuel substance because it can be broken down with oxygen, aerobically, and without oxygen, anaerobically. Alright, so without further ado, let's go straight to the first anaerobic energy system. It is the energy system that you would use for explosive events such as the discus, javelin, shot put, 100 metres, a football centre forward sprinting onto a through ball, a goalkeeper diving explosively from the middle of his goal outwards to save a ball, to tip a ball over the bar. It's explosive maximum energy. In your muscles you have ATP stored, but you also have another substance called phosphocreatine, and we can call it PC. Stored ATP depends on the size of your muscles, and it depends on the type of muscle twitch fibres you have, but you've got about enough stored ATP to last between 2 to 4 seconds. PC will give you about another 6 seconds. So potentially, the first energy system, the ATP-PC system, can last for about 10 seconds of maximal explosive intensity. The kind of maximal explosive intensity that a 100-metre sprinter needs. Now, PC, let's go a little bit more detail. Phosphate, and creatine, phosphocreatine. When the bonds are broken by an enzyme, a biological catalyst, when the bonds are broken, energy is released. It's not the energy to explode off the blocks or to run, it's the energy to rebuild ATP. Because it's the ATP being broken down that gives you the energy to explode off the blocks and to sprint for the remainder of the 100 metres. Every PC you break down, you can rebuild 1 ATP. So it's a kind of a 1-for-1 reaction. 1 PC gives you 1 ATP, or 1 cork back in the bottle. It's going to last for 10 seconds for explosive maximal events. I've put centre forward sprinting onto a through ball, a hammer thrower, a long jumper. But the best example for your exam is a 100-metre sprinter. PC is broken down by an enzyme, so it creates a P plus a C plus 1 ATP. That PC can be rebuilt when intensity lowers. But if your intensity is maximum, once the P and C are broken, you're not going to get them back together until intensity decreases. Okay, lovely. So that's the first anaerobic energy system, lasting for 10 seconds of maximal explosive activity. The second anaerobic energy system is called the lactic acid system, or we can call it anaerobic glycosis. Glycosis just means breaking down glucose, but this is anaerobic glycosis. So remember I said at the start, glucose is our golden substance because we can break it down with or without oxygen. Well, in anaerobic glycosis, or the lactic acid system, which you need to refer to it in your exam, glucose is broken down without oxygen. Why? We'd normally want to break it down with. Well, when intensity is high, higher than around 80%, there's not enough oxygen available to break down glucose. Intensity is too high. We can't deliver oxygen to our muscles quickly enough. Our cardiovascular system can't work that effectively. So we have to break down glucose without oxygen, which is absolutely fine. It gives us energy. It actually gives us energy to put 2 more corks back in the bottle or rebuild 2 more ATPs. But we have a problem. The lactic acid system is called the lactic acid system because of the problem. As well as getting 2 ATP, we get, unfortunately, lactic acid, which is why Usain Bolt would never win a marathon. If we didn't have lactic acid, if we could just sprint for 26 miles, Usain Bolt would win it. Hands down. But he can't, because if you go above 80%, generally 80%, you're going to start to build up lactic acid. You're using between 80 and 100% anaerobic glycosis for your energy. So as a popular exam question, what's the byproduct of the lactic acid system? Lactic acid. Energy? Yes, but lactic acid. How long does this energy system last for? Well, it's about 60 to 90 seconds, but that depends on the intensity of the exercise. If you're working at 100%, you're not going to get 90 seconds out of this energy system. If you're going off at about 90%, like a 400-metre runner would do, and then try and sustain that 90% top speed for 400 metres, they're going to be using the lactic acid system. Off the blocks, bang, the gun goes, ATP-PC system. ATP-PC system for the first 4-5 seconds of their run. But the lactic acid system slowly becomes the predominant energy provider. Breaking down glucose without oxygen becomes the predominant energy provider for the rest of that race. When else might a sportsman use the lactic acid system as the predominant energy provider? Well, something like a football fullback. Someone like Alexander Arnold. His goalkeeper distributes him the ball in a defensive position. He passes it in field and then he sprints. He makes an overlapping run right down the flank. The ball goes midfield players and then it goes over the top for him. He sprinted from one end of the pitch to the other. He crosses the ball. Unfortunately, the goalkeeper catches it. He's got a problem, Alexander Arnold. He's got to sprint back. So that sprint from one end of the pitch to the other, crossing it, and then sprinting back, yes, he will have used the ATP-PC system, but on his way back, the lactic acid system will become the predominant energy provider. When he gets back into his position, his muscles are going to be full of lactic acid. So he has to lower his intensity and recover so that we can get oxygen to that lactic acid. Just a note here, and it's not for GCSE PE, but lactic acid is actually not all bad. For your exam purposes, it's bad. Lactic acid stops your muscles from contracting. It makes them painful. It makes them achy. It makes them burn. It stops them working effectively. But once you're recovering, if we can get oxygen to that lactic acid in our muscles, 60% of the lactic acid never leaves our muscles. With oxygen, the lactic acid is turned to another acid called pyruvic acid. Pyruvic acid enters the Krebs cycle, and ultimately we get energy, carbon dioxide and water. So lactic acid during recovery is actually a valuable metabolic fuel. 40% of the lactic acid we create in our muscles is taken in our bloodstream to our liver, where the lactic acid is converted to protein, glucose or glycogen. Remember, that's A-level. That's just a little bit higher learning. You don't have to remember that for your exam. But it's worth you knowing as a footballer who's made that sprint and then sprinted back, suck in the oxygen, suck it in, recover, stretch, get oxygen to that lactic acid you built up, and 60% of it will become a valuable metabolic fuel. Okay, so we've got the first energy system for explosives for 10 seconds, ATP-PC system. Then we've got anything from 60 seconds to 90 seconds, depending on the intensity. We've got the lactic acid system, or anaerobic glycosis. But what is the energy system I'm using right now to talk to you? I'm not exploding with force anywhere, so it's certainly not the ATP-PC system. I've talked to you for certainly more than 90 seconds. So where am I getting my energy from to sustain this? Where does a marathon runner get his energy from to sustain 26 miles, or a Tour de France cyclist to cycle all day, or a biathlete or a triathlete? Where are they getting their energy from? It can't be the lactic acid system for all that time, because the lactic acid would stop them performing well. So we have to have an energy system which is aerobic, with oxygen, that can be sustained for a long period of time. Actually, sustained until you run out of glucose, or until you increase the intensity to an anaerobic, beyond your anaerobic threshold. Remember, your anaerobic threshold is normally above 80% of your maximum intensity. Anything above 80% of your top speed, you're going to go anaerobic. You're going to go lactic acid system. All right, but anything from 0% up to 80%, we're using glucose and fats for energy. I'll come on to fats in a second. All right, so the aerobic energy system. This is the one that marathon runners are going to use. How do we use it? Well, glucose, C6H12O6. You need oxygen, 6 of them, to break it down fully. If you can break down glucose fully, you get 3 things, 3 byproducts. You get energy, but not energy to build 1 ATP, like the PC system, or 2 ATP, like the lactic acid system. But in the aerobic system, you can put 38 corks back on the champagne bottle. 38, if you break glucose down fully. The energy yield is 19 times better than anaerobic glycosis. Aerobic system, we can call it aerobic glycosis if we want to, breaking down glucose with oxygen. So, let's go on to this. Carbohydrates are just longer molecular structures of glycogen and glucose, so ultimately they're the same thing. So, foods that are high in carbohydrates are things like cereal products, wheat, rice, pasta, potatoes, high in carbohydrates. What you do to those carbohydrates is that they're slowly reduced to glucose. The glucose is stored in your muscles and in your liver, and we break it down with oxygen when we need it. I'm doing it right now to provide energy to talk to you, to provide energy to stand here. It's a great thing, glucose with oxygen, because the 3 byproducts, energy, 38 ATP, and carbon dioxide and water are not a problem to us. We can just breathe out the carbon dioxide, and the water is not a problem. We need water for every body function. Not least when you're playing sport, you need the water for thermoregulation, to stay hydrated so your body functions properly. So the byproducts of aerobic glycosis, or the aerobic energy system, are no problem at all, unlike lactic acid, which is the byproduct of the lactic acid system. Okay, I hope you get this about glucose being that golden substance, but fats are not the bad thing that people make them out to be. Some fats are actually really good fats. The high density lipoprotein fats are good fats. The fats that are normally liquid at room temperature, we can use them as a valuable food fuel. Here's a typical fat, C6H32O2. Now you'll notice to break that fat down, there are more bonds. So potentially there's much more energy. There's a lot more. There's 129 ATP from this fat, but because there are more bonds, you need much more oxygen to break them down. So in this case, instead of 6 oxygens that you need to break down glucose, you'd actually need 23 oxygens. And that creates more carbon dioxide, more water, but ultimately more energy. So the energy yield from fats is 4 times what you can get from glucose. But because you need more oxygen, obviously, you're only going to start breaking down fats when intensity is quite low, when it's quite moderate. As soon as intensity of exercise gets up here, actually, we don't have the spare oxygen to break down fats. So then we're just into breaking down glucose. The more you train, the more aerobic you become, the more mitochondria you get, the higher the intensity you can actually perform at and stay aerobic. The higher the intensity you can perform at and use fats for energy. So a really trained athlete, aerobic athlete, might be able to utilise fats at 60 to 70% of his top speed, whereas a club athlete, anything beyond 50%, fats are no good anymore. It doesn't have the spare oxygen, which is one of the reasons why we train. Okay, so in summary, ATP is the only usable form of energy. Why do we eat? We eat to rebuild ATP once it's been broken down to ADP plus P. If you want energy to be explosive, if you want energy for those explosive events, then it's going to be provided by the ATP-PC energy system. Only lasts for about 10 seconds. No harmful byproducts at all. Just the P and the C broken down and the ATP broken down. It's not like lactic acid. It's not harmful, but once it's broken down, that's it. You can't use it again. That's why it only lasts for about 10 seconds. If intensity is still high, very high, near your top maximal intensity, beyond 10 seconds, the lactic acid system is going to take over. The problem, the harmful byproduct is lactic acid, which is why it only lasts for 60 to 90 seconds depending on the intensity. Lower if intensity is maximum. The third energy system when intensity is moderate and low is the aerobic energy system. Okay, thank you for listening.